All right, good morning. Let's continue what we started last time. So we were talking about invertible phases, invertible gap phases, and we started discussing the entire chain of fermions in one dimension as an example. And this example illustrated several properties. First of all, our non-trivial invertible phase was gapped on a closed manifold on a circle, but had gapless edge modes on an open segment. These gapless Majorana modes, and we further discussed that we can already detect the non-triviality of this phase on a closed circle, on a closed manifold, by considering its response to insertions of fluxes. And in the partition function language, we could study the partition function on a torus. And
sorry, I misremembered. I thought you had only minus sign yesterday in the
we consider the torus partition function with different state structures, never Schwartz or Ramon, and we saw that there was one sector, the Ramon sector, in which the partition function was equal to -1. When we consider the trivial theory, the trivial chain, then the partition function was insensitive to flux insertions. So that's a way to distinguish the trivial phase from the non-trivial phase already on the closed manifold. And this turns out to be a general lesson. To detect invertible phases on closed manifolds, we need to study their response to symmetry to insertions of symmetry fluxes, if we are talking about invertible phases with symmetry, and generally we need to consider arbitrary manifolds. So
can I just where did you use the fact that the phase was invertible?
So far nowhere, but it is invertible, right?
It is invertible, but why are we focusing so much on specifically invertible phases or not any other phases?
Because they're simple.
Okay.
Because they're simple, also because their boundaries carry Topological. So we will talk more about this. For more complicated gap phases, the boundaries in some sense are non-local. They don't have a local Kubert space.
Sorry, could you explain again why the edges are gap?
Why?
Yeah.
Well, so here, let's just focus on this particular model, right? So we have these two unpaired Majorana modes, and they're not involved in the Hamiltonian at all. So there are two states characterized by I gamma 1 gamma n bar equal to ±1. They are both ground states, and they're degenerate. How would you live this degeneracy? Well, you have to generate an operator like this in your perturbation theory if you added some perturbations, but you can only generate it by, you have to couple across the entire chain, and this effect will be exponentially suppressed.
Right. In this gapless, doesn't it mean that there should be a gap above those two states in the next one? So instead there isn't. So what are the small excitations above those?
So on an open chain, the spectrum looks like this. There are two degenerate ground states. Well, they're split by, in the case of perturbations, they're split like this, and then there is a gap. And in this particular chain, we had the gap was equal to some number, like 2. If you Hamiltonian this. I gamma J bar.
But in the continuum, so this gap stays constant even in the continuum, but shouldn't I have, so instead but there should be a continuum of space labeled by momentum along the boundary, like the 1 + 1.
Well, very good. But in this case, it's just one-dimensional, so this is spatial dimensions, it's a one-dimensional chain, so the boundary is just zero-dimensional system. So there is no notion of, there is only translation and time on the boundary. Other questions? So we'll see that a general feature of these invertible phases is that we want to study the partition functions on arbitrary manifolds. Now, it makes and condense some lattice Hamiltonian. How do you put it on an arbitrary manifold? It's in general very difficult, unless you're talking about the torus, which is simple. Manifolds with curvature are difficult. How do you take the continuum limit? So it's preferable to first pass to a continuum field theory, then put it on a curved manifold. So let me tell you how to do this in this simple example of the Kitaev chain. How to put Kitaev on an arbitrary two-dimensional closed manifold. And the idea is the following. So we have these two Hamiltonians. This is H1 and we have H0. This is H0, H1, gamma J bar. And let's consider a family of Hamiltonians interpolating between them. Lambda H0 plus lambda H1. Right? So we start adding initially weak couplings here, and finally we arrive here. And it's still a free fermion theory, and we can solve its spectrum exactly for any lambda. Yes?
Maybe the answer is already well. So when you have an open boundary condition, you have two-fold gamut ground state.
Yes.
In that case, is it still invertible or not?
Well, so when we discuss invertibility, we discuss ground state on a closed manifold.
Okay. So this is like should be thought of as like a probe, right? So
that's right. You cut it open to probe the phase. Eventually, we'll also be interested in the physics of the boundaries. In this case, the boundary is kind of trivial; it's just a single Majorana. But in high dimensions, the boundary has some dimensional extent, and there can be non-trivial field theories living on those boundaries. And we'll be interested in constraints that the bulk places on the dynamics of those boundaries. All right, so we can solve this Hamiltonian, and in fact we find that it's gapped for all lambda between 0 and 1 except lambda equal 1/2. So phase transition at lambda equal 1/2, and if you solve for the spectrum along which at lambda equal 1/2 actually have all these bonds are the same. And if you solve for the spectrum as a function of momentum, you find that at zero energy you have two modes. You have a right mover, right, and high left, which are one-dimensional right-moving and left-moving Majorana modes. So the Hamiltonian at low energy at lambda equal 1/2, the low energy Hamiltonian is just this. And if we turn on the small deviation of lambda from 1/2, we open up a mass gap. So H I right left, where close to lambda equal 1/2 m is something like minus 2. All right, so then we get this. The continuum limit is this near the phase transition is this massive Majorana theory, where one sign of the mass corresponds to the trivial phase and the other sign of the mass corresponds to the Kitaev phase. And there is actually a very nice way to see the Majorana edge modes in this language. Let's take this theory and let's consider a mass that interpolates in space between one face and the other, and you can solve the spectrum of this theory, and what you find is that it's gapped except for protected Majorana zero modes that sit near the place where the mass changes slightly. So these are exactly the Majorana edge states of the chain, but now seen in this continuum description.
Sorry, what's the horizontal?
X. Right, so it's changing. You can think of the vacuum here as the trivial phase with infinite mass, or alternatively, just put your H naught here. Right, we still have the Majorana edge mode left, and this is exactly what we are doing here, but in the continuum description, and we see that the boundary between the trivial and the entire phase has a Majorana.
So is there an advantage to including that extra bit as opposed to just considering the system on a space with a boundary on an interval?
It's just a little bit easier to think about the boundary condition here.
Okay.
Questions? All right. So now that we have a continuum field theory, and it has an emergent Lorentz symmetry, we can put it on a curved manifold. Right. So let me rewrite this in a Lorentz invariant way.
So, Max, the statement here is that there is only one zero energy state independently of the profile of M of X?
Not quite, but you are guaranteed that the number of zero modes here is odd. Yeah.
You can have more than one.
You can have more than one in principle, right? I mean, it depends on your, you could depending on how you do your edge, you could.
Is it exactly the number of zeros?
I'm not sure in this case. Sometimes there are theorems that guarantee that there is exactly one. I forget. Right. So let's write this in a Lorentz invariant manner. So in flat Euclidean space, we would have a here is our Majorana fermion. With the standard and now
So
this
just a rewriting of that.
that's just rewriting. That's a Hamiltonian. This is now a Lagrangian. I'm just kind of setting up the Lorentz invariant notation. But so now that we have a Lorentz invariant theory, we know how to couple it to gravity. We can put it on an arbitrary curved manifold. Now, because we are dealing with fermions, we will need a spin structure to put it on an arbitrary curved manifold. But let me kind of take that as as implicit. And well, we will end up with an action which will be, you write it like this, e to x, g, phi, where this d is the generalization of the Dirac operator to a curved manifold. Let me not write it out explicitly.
Sorry, is there any difference between this and the 2D model?
2D easing model.
Yeah.
So, very good question. So this is a almost none, right? So this is a 1 plus 1 d Majorana fermion
Yeah.
CFT, which is a spin CFT. If you sum over the spin structures, you get the easing model.
So okay, so this Hamiltonian or the Lagrangian is implied that the current symmetry that flips the mass. So the point is that in the bulk, the two phases, the Kita phase and the trivial phase are indistinguishable.
That's the Kramer's one year.
Yeah, that's the Lagrangian
Symmetry.
for easing, and it acts non-trivially on, like the fact that on the boundary in one case you have edge modes and the other case you don't, is because the Kramer's one year acts non-trivially on the boundary.
It essentially, if I'm not mistaken, the presence of edge modes actually corresponds to your in one phase there's a twofold degeneracy due to the symmetry breaking,
Yes.
and that's I think reflected in the twofold degeneracy of the ground state in the fermionic system on an open chain. On a closed chain, you have to be more careful. You have to. There are different symmetry sectors in the Ising model and different flux sectors in the Ising model, and then there are different spin structures in the fermionic theory, and then there is an exact correspondence that I can write down, but perhaps a bit more than will take us further afield. Other questions? All right. So the partition function of this theory on an arbitrary manifold M, right, is it's formally just the Pfaffen of this operator Now, what can we say about this operator? Well, first of all, this slash is minus ID slash is Hermitian. Second, there is an anti-unitary operator that it commutes with, which is this charge conjugation times complex conjugation. K commutes with minus ID. K is just complex conjugation, and CK squares to minus 1. So this anti-unitary operator squares to minus 1. That means that for every eigenstate of ID, there is a linearly independent state C phi lambda star with the same eigenvalue. So then, if I expand my Majorana fields in terms of eigenvalues of ID, in terms of these pairs of eigenvalues, phi lambda and c phi lambda star, the matrix C dagger, well, by action essentially becomes like this. One, two, transpose. So the partition function is just a product of patterns of these 2 by 2 matrices. So M is equal to product of lambda I lambda plus. I should put product with the prime because in this product from every pair of eigenvalues like this, I will just count one eigenvalue.
Did you want to put C on the second term?
Yes, thank you. All right. So this is a partition function that we can regularize in some way. But the interesting point is how to regularize the phase of this partition function, right? It's some product of some complex number, so there's a phase. And in this case, there is a very natural way, actually, to regularize this partition function. Remember, we have two phases, one with positive mass, one with negative mass. The phase with one of the signs of the masses is a trivial phase, which is continuously connected to just a product state of the wave function, the ground state wave function, which is just a product state. Now, for such a trivial phase, we expect, so let's call m greater than 0 the trivial phase. We expect that the partition function up to local counter terms involving the curvature of the manifold should just be equal to 1. So then, to define, to regularize the partition function of the non-trivial phase, we might just divide it by the partition function of the trivial phase. So consider Z regularized of M, the product of lambda M. Very nice. All right. And now this further simplified. Another property of this Dirac operator is that there is a matrix gamma 5, if you wish, or gamma 3 in this case, that anticommutes with D. So for every eigenvalue lambda that's positive, there is a corresponding eigenvalue minus lambda. So this sum over lambda, this product over lambda, I can write as a product of a positive lambda, and then include the negative part. And this product is just 1. And in addition, there are contributions from the zero modes. And the zero modes just contribute -1 to the product. So that this whole thing just becomes somewhere separately. with -1 to the number of zero modes of the operator over 2. Right? Over 2 because we count, because of this prime, we count the eigenvalues, we count each pair once. Okay, so this partition function, we see, is actually just equal to plus or minus 1. And furthermore, this partition function is a topological invariant. Why is it a topological invariant? Well, remember, first of all the eigenvalues lambda come in pairs, phi and c phi star, and then for every pair of positive eigenvalues, there is the corresponding pair of negative eigenvalues because of the gamma bar. And, okay, now the partition function counts the number of zero modes. So suppose there are some zero modes. And now we imagine that we change the metric on our manifold. What happens to the number of zero modes? Well, what can happen, say, is that 2 eigenvalues from above descend and 2 eigenvalues from below descend. They always come in pairs. So overall, the number of zero modes will change by 4. So the partition function will not change. So that's why it's a topological invariant. Yes?
Sorry, in the last line there, should there maybe be a plus sign in one of them?
I think you're right.
Okay.
Yeah.
Other questions?
Prime again?
Sorry?
What else?
Well, the prime is all eigenvalues come in these pairs, and we're counting, for each pair we're counting it only once. Yeah, that's the prime. Other questions? Yes.
In this language, is there a simple way to understand why the partition function is also be a cobordism invariant?
The APS theorem.
Yeah, but I'm trying to understand whether there's simple, let's say, path integral type arguments.
I'm not. Let's leave those questions for later. We'll discuss that this is a Bordism invariant, then we'll talk about Bordism, and then we'll try to ask why Bordism. Okay.
Sorry, at some point you said, okay, let's take the mass greater than 0 to be the trivial phase. Is that a convention? Because
It's a convention.
So
It's a
pick
convention.
one, and then so it's the regularization is what tells you what you call the non-trivial phase, and I call
That's correct. That's correct. Yes. In the continuum theory, there is no other way to do it. On the lattice, you can. On the lattice, there is a notion of what the trivial phase is, just the product state, and we can. All right. So this is a topological invariant. So here is an example, one that we are already very familiar with. Just a two-dimensional, take the manifold to be the two-dimensional torus. And as we discussed, there are 4 different spin structures on the torus. But independent of that, well, what is the spectrum on a torus of the Dirac operator? Is left, right? It just minus I d tau gamma tau plus t1 gamma 1. So we can go to momentum variables. This will become k tau gamma tau plus k1 gamma 1, and the eigenvalues are plus minus square root of k tau squared plus k1 squared. So to have a zero mode, k must be, both k tau and k1 must be 0. And the spin structures, the boundary conditions, say that case, the momenta are either integer or half integer in units of 2 pi over the length of the torus direction. So in the half integer case, we are not going to get 0. So it's only when we have periodic boundary conditions along both directions that k can be 0. So that's the Ramon sector. And then, well, we just want to look at the constant spinors. Those are the 0 modes, and there are 2, right? There is chi right and chi left. So there are 2 0 modes, and the partition function z of minus m, Ramon, is equal to -1. In all the other sectors, if you have at least one Leva-Schwarz, you get +1. There are no 0 modes. So that exactly agrees with our discussion in the lattice model. That's nice. What about the boundary of so far we consider the manifold which is closed. What if we consider an open manifold? Well, we already saw that there is a Majorana mode living on the boundary. Here is a action for the 0 + 1 dimensional Majorana mode. So the partition function of this boundary Majorana is nominally just the Pfaffen of dd tau.
So gamma is just a new degree of freedom. It's not.
Gamma is a new.
It's not directly coupled to the bulk field that you call
here, let me just discuss the gapless degrees of freedom on the boundary. If you wish, I can start with my domain wall and just focus on the 0 mode that lives on the boundary. So for this Majorana mode, the question is how to define this Pfaffen. With Pfaffen, there is always a question of what is the sign. And in the bulk, well, we also had a Pfaffen, but we had a mass term to regularize the Pfaffen and to define the phase. In this case, there is no mass term for this Majorana that we can write down. So the sign of this partition function is ambiguous. The other problem is that, well, depending on what the boundary condition around this circle is, Leva-Schwarz or Ramon. If it's Ramon, there are 0 modes. So then we are kind of off the hook. The Pfaffen vanishes, so we don't care about its sign. But we could ask about correlation functions. Say, you have a manifold with many boundaries. There is a 0 mode on each boundary. Say there are several Ramon boundaries, and you can ask, in the path integral measure, how are the 0 modes from different boundaries? How are they ordered? Changing the order in the Grassmann path integral measure changes the sign, right? So this would be relevant if you compute some kind of correlation functions involving the boundary Majorana. So what are the answers to these questions of science? And the answer is the following, at least for the, so first of all, these questions can be answered, and it turns out that for the, at least at the level of the partition function, this is the answer. And there is other question of how to, we have this bulk partition function on a closed manifold. Well, what is the generalization on an open manifold? What does the bulk contribute? You have to say what are the boundary conditions on this Dirac operator if we're going to try to use some generalization of this formula. And turns out that the answer is that you still, so first of all, the boundary contributes this pocket, this absolute value. The bulk contributes again -1 to the number of zero modes of the bulk Dirac. So this is a two-dimensional Dirac operator. But the boundary conditions for this Dirac operator are the so-called non-local APS boundary conditions. Non-local. Why this is the correct prescription on an open manifold? In particular, why do we get these non-local boundary conditions? Shouldn't all boundary conditions be local? Well, you can actually derive it from local boundary condition. And it's discussed in this paper by Witten and Yonitura. I will not discuss it in a lot of detail, but basically this is kind of our first example of non-trivial matching between the bulk and the boundary. The bulk contributes something that by itself, is probably is non-physical because of this non-local boundary condition on D, and then the boundary contribution, which will be kind of ambiguous in terms of sign by itself. You put them together, you get something sensible.
Did you say something about how non-local they are? What do they?
So I can talk about it a little bit. The idea is that there is a bulk Dirac operator. You write it near the boundary as some, there's kind of a time, gamma tau, d tau plus some d boundary, and you allow only the modes, when you restrict the bulk wave function to the boundary, you allow only the modes that are composed of positive eigenvalues of d third. This is the APS boundary condition. If you wish, these are the solutions that if you extended this color out to infinity, they are zero modes of d slash that would be normalized.
So this is non-local in the sense that you need to know the whole boundary in order to fix them, or
you need to know this, right? It's somehow in terms of the spectrum of the boundary. The chi restricted to the boundary has to belong to H plus of d slash per, where this H plus is the Hilbert space of positive eigenvalue modes of H.
sort of follow-up question. So that these boundary conditions seem to make sense also if I have only one boundary. Like if I took this manifold and close it off smoothly on the left, I could still consider one boundary.
You can,
Yeah, this.
you can consider this.
And what is the relation with respect to last time you pointed out that since on open chain I have two Majorana modes and there's a Hilbert space that is anomalous as square root of 2. So this partition function should
This
count
partition
them.
function will be root 2.
Should be root 2.
If you don't worry about, if you just regularize the Pfaffen on the circle, let's say you use what's it called, zeta function regularization, you'll get root 2. Yes?
So this boundary condition, say in the Fermion description would be non-local, but in the TQFT language, it would still be a local kind of boundary condition.
I think on the cobordisms it does. So if you compose then this thing is added. That's my other questions? So
Can this be derived from a lattice local Hamiltonian?
So the fact that the partition function looks like this, if you impose local boundary conditions in your physical theory on the boundary of the manifold, is actually derived in this paper. It's a very nice thing. So let me go back to the bulk, and this was our bulk partition function, and we said that it's a topological invariant. Now there is actually something that she already pointed out. It's not just a topological invariant, it's what's known as a Bordism invariant. And this turns out to be very generic.
Sorry, can I ask you one question about the perturbation from the fixed point, say the vanilla case of that space? So there's Kramers-Vanier in the bulk, but there's also plus or minus boundary conditions for the fermions on the boundary. Maybe you already answered this question before, but so there is an invariant statement, right? If I turn on the mass with a certain sign and starting from conformal boundary condition, which has either plus or minus, Kramers-Vanier acts on both, so that there is an invariant product. So
you mean boundary conditions that break the Ising symmetry?
Yeah. So break chiral symmetry exactly. So this is like a psi.
No, there is Ising symmetry and there is Kramers-Vanier. Those are two different symmetries.
Yes. So let's see. I think you can fix psi, the bulk psi for plus or minus psi bar or something like that. So there's two choices of boundary conditions which are natural in the free fermion. And since Kramers-Vanier acts on psi bar and doesn't matter, or in this case acts on chi right but acts on chi left, then this sign is flipped by Kramers-Vanier, which also flips the mass. So there is an invariant statement which is a pair of a certain sign for the perturbation away from the critical point with a certain boundary condition of the two. And so I was wondering so then it means that I can unambiguously flow towards either a trivial phase or the non-trivial phase if I have a boundary. And I was wondering what's the feature of the critical point that tells me, like these two boundary conditions have different spectra, which one will be the one that gives me the trivial or non-trivial phase? But what is the avatar in the critical phase of the fact that there is that?
I think you probably only have the relative, right? You can one boundary put.
One boundary with one mass exactly.
And the other boundary with a different.
And the other boundary with the opposite mass. But so that's invariant and it's physical, and I don't know, like if I give you only the critical theory, can you tell me what sign I should choose, what relative sign I should choose to flow to the gap to the trivial phase, and what relative sign I should choose to flow to the non-trivial phase?
Right, so in one, so first of all, if you have CFT, if you have one and the same massive phase on the right and the left, then the boundary conditions will be such that there is even if you have zero modes, there will be an even number of them. If you have a single Majorana mode, that is, then that corresponds to having mass say positive here and mass say negative here.
But why do I need to talk about two boundaries? I mean, since already the dimensional disk also makes sense. Why can't I just take a PCFT with only one boundary? I fix the boundary condition and the small perturbation in one direction, and I ask if I flow with that perturbation, do I get square root of 2 or do I get 1?
Yeah, so there is, in this language, I think I know what you are talking about. So you can ask, there's a general question. Let's say take ZCFT, right? And you answer it with ZTQFT. Sometimes this is actually the same as the CFT. That is, the CFT partition function vanishes whenever, so this is on closed manifolds at this point. The CFT partition function vanishes whenever the TQFT partition function is non-trivial, not equal to 1. And this case of Majorana CFT and Majorana gap Majorana chain is an example like this on a closed manifold. On an open manifold, I forget whether it's still true. We can discuss it.
Yeah. Okay. Thanks. Sorry.
It's not always the case. There are some. So it's actually an interesting problem. What, given a TQFT, what CFT can eat it like this? Yes. So it turns out that this partition function is a Bordesman, on a closed manifold, is a Bordesman variant. What does it mean, Bordesman variant? Bordesman variant means the following. So we need to define this idea of Bordesman. Say you take two d-dimensional manifolds, xd and yd closed. We say that they are Bordant if there exists a d plus 1 dimensional manifold d plus 1 such that dm d plus 1 is equal to the boundary of this md plus 1 is the union of x and y with its orientation reversed. So basically, here is the prototypical picture of pants. Right here is your manifold X composed of two circles. Here is your manifold Y composed of a single circle. Here is a two-dimensional manifold M that interpolates between them. Okay.
What's the white bar on the picture?
So you have to, these are the orientations, right? So 2 copies of x is bordered to y. If you take the boundary of M, then you get y with the orientation reversed.
You have y, there's a bar above, what's the notation? Can you remind me of that?
This is y with its orientation reversed. So we say that the partition function is a Bordian invariant if z of xd is equal to z of yd when x and y are Bordian. And it's actually believed that Bordian invariants classify all invertible gap vectors. Okay.
Sorry, this means that if this property is true, you expect the theory to be invertible?
That's right.
Is there a simple intuition for this? It looks like a very different definition.
Well, let's go a little bit further and the inverse will just be, the inverse theory will just be one which will assign z star to x. And these are going to be phases, and then the product is just one. So, actually,
So far it's okay without symmetries.
we can put in symmetries. I'll explain how to put in symmetries in a second. So, actually, D manifolds with Bordism form an abelian group. Omega D. The addition in this group is just the disjoint union of the manifold. The zero is the empty set. And the inverse is the manifold with its orientation reversed. Right? Why is it an inverse? Well, here is the manifold, here is the inverse, here is the manifold with the orientation reversed. I can always do this. Here is the empty set. Here is the Bordism. X disjoint union minus x bar is Bordism to the. Now our partition function should assign numbers to closed manifolds. And first of all, it should under this joint union, it should give us product of partition function, right? Partition function of the disjoint union of two manifolds is just the product of the partition functions on each manifold. So, if a partition function of a board of the theory is a Bordism invariant, then it should be a homomorphism from this Bordism group to C. This is just exactly the homomorphism condition, because remember this joint union is the addition operation in the Bordism group. Now, okay. Unitarity says that the partition function on the manifold should be the complex conjugation of the partition function on the manifold with its orientation reversed. So, that
You never talked about unitary central.
that's correct.
Don't you want to justify this with?
Justify this statement?
Yeah.
Well, this is let's see. On a simple, let's see. Psi minus H T phi is I think the basic point this is the statement of reflection positivity at the level of partition functions. Well, it's a weaker statement actually than reflection positivity. Can make this particularly right, so in other words I think this is what underlies this statement.
So the arrow is an equal sign, I guess? Check, I can make it with an equal sign.
Excuse me?
Where you put the arrow, you just redefine, like you flip the old figures so those two are equal.
That's right.
Okay.
That's right. These are the same. This is manifold with one orientation. This is manifold with opposite orientation. And that's essentially what underlies this statement.
Sorry, should one of them not be complex conjugate?
Looks like they're both star.
No, but they should be equal star.
No.
It's just what's inside the star has been just drawn in the other.
I'm just redrawing this in the other way,
Okay.
right? And I'm saying that this.
Oh, okay. Okay, thank you.
This, oh, yeah.
Sorry, can I ask, earlier you said Bordism invariants classify invertible phases, and I just want to know if the precise version of that statement is that, so homomorphisms from omega d to c form some group, and that group is precisely the list of groups that you wrote earlier that classify invertible phases. Is that right?
Almost. I'll make it more precise. Actually, the torsion of that group is what matters, and then the free part actually corresponds to the free part in one higher dimension. So I'll talk about this right now.
There is sometimes it is about like, so, for example, let's take circle.
Yes.
Circle is diffeomorphic to the circle with the orientation reversed.
Yes.
So should I then conclude that partition function of the circle should be real?
Correct. In fact, well, in one dimension, without symmetries, for bosons, there are no invertible topological phases. So
Why it wasn't? Why it suddenly wasn't?
we'll talk about what kind of structures on the manifolds you have to think about. So far, I've been very inclusive. Now, from this statement, well, if that is a Bordism, if that is a Bordism invariant, right, this should be equal to 1. So z of x, z star of x is equal to 1, so z has to be x. So this comes back to your question last time, why phases? So this is one reason. Of course, the much better question would be why Bordism invariant? And maybe next time we'll talk a little bit about it.
The statement that the TQFT has a one-dimensional Hilbert space, is that a consequence of that the current function is Bordism invariant, or is it after some factor?
It's a consequence, I think. Let's see. You can the partition function on like this, right? You can always shrink the disk to a point. So it's always is the boundary of xq minus 1 cross g. So it has to be. You can actually, there is a more interesting question. Can you use no degeneracy on any spatial manifold to prove Bordism invariance? And we can talk about that. Yes, Matthew?
So if two manifolds are Bordism equivalent, are they always topologically equivalent also?
No.
Okay.
Bordism equivalence is much stronger statement than topological.
Yeah, I guess that's the confusion. So you just gave this simple example that x be connected to x bar by a cylinder.
Yes.
Well, so that's a very restricted kind of bordism.
There are
And now from here you want to go to basically arbitrary bordism, which can be very, very complicated equivalence transformation.
Why does the
just because just out of the two very simple properties that you can consider this simple cylinder bordism. I mean, there are many other types of bordisms that one could imagine for which these properties could be true, but why should they be true for maximally complicated?
You're asking why should the partition function of a gap theory, gap invertible theory, well, of an invertible theory be a bordism invariant?
For arbitrary bordisms. Like for
arbitrary bordisms.
There could be some restricted types of bordisms for which this might be true. This looks reasonable, but why for arbitrary?
Let's talk about it next time.
Very.
It's a great it's a great question, and there are not a lot of answers in the literature, but there is some maybe there is a little documentation that we can do.
Okay.
All right.
Can I ask a question about this? So the fact that Z is a phase here, I mean, it's we said last time. You said last time that this depends on some local counter terms. It's there's some real parts that you can cancel, etc. So what of this statement depends on unitarity? Probably does not. So it's bordism invariant if you define up to local counter terms.
Bordism invariance. I think you basically need the partition function on SD to be equal to 1. You set the partition function on SD equal to 1, and after that, all right. So, what kind of manifolds should we be working with? And that turns out to depend on what kind of phases we are interested in. So, for bosons, if you're interested in phases of bosons without symmetry, well, bosons without symmetry, it should be possible to put the theory on an arbitrary oriented manifold, and the partition function can depend on the orientation. So we think about manifolds with orientation. And we think about the bordism group of manifolds, of d-dimensional manifolds with orientation, which is known as omega DSO. Fermions without symmetry well, we need a spin structure to put a fermion on a manifold, so we think about the bordism group of manifolds with spin structure. So basically, if I have my bordism, I have my two manifolds, XD and YD, with spin structure. The manifold MD plus 1 should also have a spin structure that restricts to the spin structure on the bound. What if I am interested in theories with some symmetry group G, which is unitary? Symmetry. Well, I should be able to consider partition function of the theory in the presence of background G gauge fields. So now these manifolds can have some gauge fields living on them, and then my bordism should, my manifold MG plus 1 should also be equipped with a gauge field A that restricts to the gauge field of the bound. So now the partition function in the presence of the gauge field should be a borders invariant. So I guess I'm almost out of time. Let me take 3 minutes to give some examples that this actually seems to work. So let's discuss various dimensions, various kinds of phases. So examples. Bosons.
Sorry, when you say that the partition function with the background gauge field should be borders invariant, do you assume that, are you requiring that you can extend A into the bulk in such a way that the gauge fields agree or something?
That's right, that's right, that's exactly it. So let's discuss bosons in 1 plus 1 dimensions with no symmetry. What is the Borders group of oriented two-dimensional manifolds? It's trivial, right? Any two-dimensional manifold can be filled in. Any oriented two-dimensional manifold can be filled in. Is a boundary of some three-dimensional manifold, so omega 2SO is trivial, so no non-trivial phases.
Sorry, what is SO?
This is the notation for Borders group of manifolds with orientation. SO refers to the structure group of Lorentz transformations in this case.
Did you need to write 0 or Z?
I wrote Z1.
Oh, Z1.
C1.
I don't know, I can write 0. What about fermions? Yeah, what about fermions in 1 plus 1D without symmetry? By the way, this disagrees with known result. In 1 plus 1 dimension, you can prove on the lattice that all gapped phases, that there are no non-trivial gapped phases on bosons without symmetry. So this is actually a theorem, and it agrees with our classification theorem. What about the fermions in 1 plus 1D? Fermions in 1 plus 1D, no extra symmetry other than fermion parity. So the Borden group of two-dimensional manifolds with spin structure turns out to be Z2, and it's generated by a torus with Ramon-Ramon spin structure. So any other spin structure, you can, on the torus, you can make the torus a boundary of a three-dimensional spin manifold. With this spin structure, you cannot. So, and then, well, it's a homomorphism, right? From the partition function is a homomorphism from Z2 to U1, which just assigns to this generator minus 1. So Z of E2 Ramon is equal to minus 1. Well, that's exactly how Kitaev chain. Remember, it had exactly this property that on the torus with
You should try to
Ramon
conclude.
spin structure, we get minus 1. Yeah, almost done. And then there are many more examples with symmetry, with time reversal symmetry in various dimensions, and everywhere things seem to agree with what's known using this Borden classification seems to agree with what's known using other methods. So next time we'll talk maybe a little bit about why Bordism. We will talk about phases that have non-trivial Chern-Simons terms, and we will start talking about digraph Newton type